So starting today, we'll get into some more details of the expressions which we began in the last class, talk more about the underlying representation of integers, of floats, etc. that help you deal with the computation of the expressions. What kind of operations do those representations undergo in order to evaluate expressions? So whatever we've been discussing so far has been largely based on chapter 3 of Professor Abhiram Ranade's book. So recap from the last class. In the last class we talked about types of variables, and if variables have different data types, what the implication is on the outcome of computation. So x into q. So if x is of type A or variable A, for example if it's int short or unsigned int, and q is of type float, double, etc., then the result of the multiplication will correspond to the more expressive type, which is say float or double. Some types require less storage. We already seen that short, float, etc. respectively require less storage than int or double respectively. So again, if you multiply a short type with a long type, the result will correspond to the long type. So int short, unsigned int, in the last class we also said these are also called fixed precision, and float double are basically floating point or floating precision. In this course we largely make use of int and double. So recap that when you have an assignment statement, you look at the assignment statement in three parts. The expression on the right hand side is what you compute first. So the expression has to be assigned to the variable name. The expression could involve pre-specified variables, operators such as multiplication, division, etc. Now we will understand a little bit more on how the operations could interplay. In particular, multiplication and division have higher precedence than addition and subtraction. Between multiplication and division they have the same precedence. So summarily we are saying that multiplication and division take precedence over addition and subtraction, and if you have multiple operators of the same precedence, they will be evaluated left to right. All this becomes a lot more convenient if you think in terms of evaluation trees. So let's look at some evaluation trees. So if you have 5 into 7, you could express this as follows. So we have a small tree, multiplication at the top and 5 and 7 as the children. 5 into 7 minus 3. Now you have to start looking at the precedence. So what has precedence here? Multiplication. So you build bottom up, 5 multiplied by 7 minus 3. On the other hand, if I had 5 into 7 divided by 3, what would I do? Yes? I'll do this processing left to right. So recall that we have operations, if they are of the same precedence, they should be evaluated left to right. So again it will be 5 into 7 divided by 3. I could also have parentheses. Now parentheses basically are these pair of opening closing brackets. Suppose I have the same expression 5 into almost the same expression, I just put this parenthesis 7 divided by 3. What will this correspond to? Now parenthesis take the highest precedence. Anything within the parenthesis has to be evaluated separately as a kind of independent expression. So you'll have 7 divided by 3, the whole thing multiplied by 5. Is this clear? So let me give you a problem. So the expression is (5) divided by 6 into 24 plus 9.0 divided by 6 into 9 minus 3. Now not only do we have operator precedence to consider, but we also have types to be considered. Okay, so we need to understand the types here. So for type, I'll do this next slide and then you'll try and answer this question. So this is again a recap. When you want to store numbers of one type into a variable of another type, C++ does something very intuitive. The first idea is what we discussed earlier. If you have a lower type into a higher type, the result will be, okay, we saw that example. That's intuitive, because if your lower type is 2, higher type is 3.1, you would actually expect the answer to be 6.2. However, if this might create a problem when you have, say, 2 divided by 3. Now both are int. So that will be interpreted as an int. So let's take this example. X is 2.5, Y is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm taking a slightly, since X is int and the value I'm assigning is 2.5, what will happen? You will basically be casting it into an int. This process is called, this is an implicit process of casting. Okay, we will see more on casting later. The fractional part is dropped. Now what will happen to Y? Y is a float. You can assign an integer value to a float, but what happened? 1, 2, 3, 4, 5, 6, 7, 8, 9. How big is it? It's a significantly large. So you might recall in the last class we talked about significance, right? So if you actually try and store this value within 7 bits, you will not be able to. So recap, for float you have a significant up to 8 bits, and that unfortunately will also include the sign, we will see that later today. Then e raised to, or 10 raised to, which is denoted as e, some 24 bits. Okay, this is 8 bits followed by 24 bits for the exponent. So it turns out that 1, 2, 3, 4, 5, 6, 7, 8, 9 cannot be precisely represented in 24 bits, the exponent part. So as a result, what would happen is that the last 2 digits will get dropped. 8, 9 will get dropped. 1, 2, 3, 4, 5, 6, 7 to 10 raised to 8. That's the maximum you could store in actually 7 bits. So 8 bits are for the case of float. Eight bits including sign, which we will see today, e raised to 10 raised to 24 bits. So e raised, that is e 24 bits. Is that clear? Actually it's 23 bits because once again in 24 bits one is preserved for the sign. Okay, so just to give you an idea that there are multiple factors playing a role here. What you are storing as what? The operations between lower and higher will result in higher, the higher in the sense more expressive, and then there is also the operator precedence. Okay, so this last point may not be very relevant for this expression, but with all this ammunition, now please try and write down the tree in case you haven't already done that. Yeah, so you'll have to actually write down in binary expansion. So somebody is asking, how do you know that doesn't fit in 24 bits? Well, you'll have to actually write down the binary representation. So we'll see how to write binary representation little later today. So what I want to impress upon you here is, you are actually constrained by the programming language constructs, its internal representation, all that matter. You cannot be just naive consumers of computers. I'll write programming, I'll write programs in a language and everything should be as I expect. No, it all depends on your understanding and appreciation of the limitations, the precision constraints that the computer has. Yeah. Sorry? Yeah. Yeah, so you'll have to basically do the binary representation. As I said, so only when you do that, you'll, not just by observing it. Float y equals 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, but if I print, you will see the second value as well. So I'll comment it out. 1, 2, 3, 4. Oh, I did. Yeah, 1, 2, 3, 4. Anyways, it has rounded off to 7. You could see that, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 has become 1, 2, 3, 4, 5, 7. In fact, it has even rounded off the 6, 7 to 7. Okay, so when you have questions, just try writing code, see for yourself. Okay, what about the first part? So the question I asked earlier, what will be the output of this operation? Okay, sorry, let me use a board. Let's write down the expression. expression tree. So what will you do first? Where will you begin? Huh? 9 minus 3, you could begin here. So 9, so yeah, brackets is, parenthesis is what you could get started with always. And then what do you do? Left to right, because you have division and multiplication. So 5 divided by 6, this whole thing into 24, and then you have an addition and a multiplication. What takes precedence? Multiplication. You can't just do left to right. So 9 minus 3, another multiplication. I'm sorry, you'll have to do division followed by multiplication. So it will be the same basically. So 9.0 divided by 6. Now let's write down the types. This is an 5 is an int, 6 is an int. So what should be the result of division? Int. So what will be 5 divided by 6 as an int? 0. Then 0 is multiplied by an int 24. What is that? 0 again. Let's look at this part, the right side. 9.9.0, right? That is a float. 6 is an int. So what will be the result? A float. What will be the what was the operation? Divided by. What will be the result? Yes, 1.9 minus 3. So again this is straightforward. Int minus int is an int, that is equal to 6. What happens when you multiply a float with an int? Float. 1.5 into 6 is again and then 9 into 0, 9 plus 0. So the result will be a float, but we'll skip the decimal part. So let's verify what the result is going to be when you program it. Okay, so it's a 9. This is what we concluded last class with, but we'll just have a relook at this problem. I want all of you to write down the expression tree with all these annotations. And what I want you to do is imagine that you will be writing this the parts of the expression tree as comments. Okay, we want you to get habituated to writing very nice comments. Okay, so comments that are meaningful, that will ensure the correctness of your program. So we'll have x as an int divided by y as an int. The result should be an int. So substitute the value of x and y, 2 and 4. Okay, you can fill in all the values. This is 0, this is a 1, and this will be a 1 int. You could likewise also evaluate x plus y the whole divided by p. So x as an int plus y as an int 2 plus 4 will result in an int 6, which you divide by p, which is 3, an int, result will be an int, but in this case it will be 2. Okay, could we proceed? Any questions up to this point? So output will be 1 followed by 2. Okay, so you could write comments like this in your code. Python, interestingly, has some different kind of syntax to accommodate specific kinds of divisions. So x divided by y is what you would expect. 360 divided by 100 is say 3.6. So unlike here, unlike C where the type of x and the type of y will determine the output, in the case of Python, the output is basically decided based on the type of the output value. So 3.6 is going to be float. However, if you wanted to do integer division, then you could do this double slash, and the double slash will basically result in integer division and doesn't correspond to comments unlike C++. Okay, how many of you have coded in Python? Here, some of you have. Okay, only 3. Yes. This is a side remark anyways. Let's see more examples. Unless you want me to do this carefully, I'm just going to make some comments, passing remarks. So D angle, anything prefixed with D is basically a double precision, but the type of the left, what you are assigning to, is not necessarily going to determine what the expression itself gets evaluated to. So you don't necessarily start with the left hand side, you start with the right hand side. So 360 divided by num sides. What is num sides? It's an int. So this would be an int, 360 divided by 100, which will be 3 plus 0.45 will be 3.45. However, now you take note of the type of D angle, and D angle is a double and therefore can be assigned the value 3.45. You have exactly the same expression on the right hand side in the second case. So you will have 3 plus 0.45. However, I angle is an int, a type int, and therefore will be assigned the value 3. Okay. So you could likewise look at the second pair. Here 360.0 is of type float or double. Float is fine, and therefore the output, the result will be again of type float, 3.6. To that you add 0.45, you get 4.05. Okay. Lab 1, you had this problem. You had to convert centigrade into Fahrenheit. You took as input centigrade from the user, and the conversion was based on this formula. While evaluating the right hand side, you have to ensure that centigrade is kept as a float. If you don't do that, then the right hand side will be evaluated to be an int. I mean, of course, unless you have this 9.0 and 5.0 explicitly put there. If you don't, irrespective of what the left hand side is, you may say, "अरे float तो मैंने, so Fahrenheit तो मैंने float में लिखा है, फर्क नहीं पड़ता, right hand side सही float होना चाहिए." So to ensure that float of Fahrenheit float is useful, you need to ensure that the entire right hand side is evaluated to be a float. Okay. So we have seen some data types so far. In C++, you have the character, character has 1 byte allocated, that is 8 bits. Float is allocated how many bytes or how many bits? 32, and that's also called a word. 32 bits is also called a word. And I already made this comment in the last class. Again, we illustrated that for an example, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. We saw that there are 8 bits in the exponent and 24 bits in the significant. On the board I reverse these two. 24 bits and 8 bits. 8 bits in the exponent, 24 bits in the significant. So though we write it as 8 bits, 24 bits, it's basically X, E, Y, where X can be up to 24 bits and Y can be up to 8 bits. In the case of double, there are 2 words which is 64 bits long. The same expression X, E, Y can now accommodate Y of length up to 11 bits and X of length up to 53 bits. Okay. So our 1, 2, 3, 4, 5, 6, 7, 8, 9 in the case of float was expressed as 1.23457, and that's what we saw in the program, right? Into 10 raised to 10 raised to what? 8. Okay, so X in this case was 1.23457 and Y in this case was 8. Okay, however, if you had stored that entire integer as a double, what would have happened? So I want you to think about it. What would have happened had I assigned this value to a double? Double has double the capacity. So float large. This is the name of variable. 1, 2, 3, 4, 5, 6, 7, 8, 9 versus double large double equals 1, 2, 3, 4, 5, 6, 7, 8, 9. What would be the difference? Would you expect the double to be able to store this value? Do you want to try it out? Want to try out the program? Yes or no? Let's try that. So the number is too large even for double. Maybe you want to try things out yourself. This is just to get you thinking about what kind of storage is really required. Yeah. Why would you? Yeah. I mean, you have to think about it. I don't want to give all answers here. Is the number just by adding or shifting by, or rather, adding two really large numbers, 10 raised to 9 and 10 raised to 10 of that order? We should we be able to accommodate the additional whatever overhead in 2 words, right? So the 2 words are basically corresponding to binary representation, whereas this is a decimal representation. So let's get down to the representation and then revisit this problem sometime. Before I move on to representation, there is one more type I want you to be aware of, which is unsigned. I've been making some remarks such as the following. We said that when you have 8 bits for the exponent and 24 bits in the mantissa, it's effectively 7 bits that are used for storing the value and 23 bits in the case of mantissa. One bit is used for storing the sign. One bit is for storing the sign. So I want to be able to distinguish between, say, 1, 2, 3, 4, 5, 6, 7, 8, 9 and minus 1, 2, 3, 4, 5, 6, 7, 8, 9. So unsigned int says, well, I don't really want to provision for the sign. I'll always expect positive integers. Okay, so it's 32 bits. So unsigned int says I'll have 2 raised to 32 values that I can store, which are all greater than or equal to 0. Right? On the other hand, signed int how many values will it store? 2 raised to 32. Right? But now we'll now ask how many of them will be greater than or equal to 0, non-negative. How many will be negative? So let's proceed with these questions in mind. So how are all these types represented in memory storage as bits? How are operations on all these types performed in terms of bits? And the answer to these questions can be sought in chapter 2 of the book. So we'll keep referring back to this chapter 2 occasionally. We didn't begin with chapter 2 necessarily because we wanted to get started with programming. You start getting a feel of programs and then you become curious on what really is happening behind the scenes. In the last class we made a passing reference to radix, okay, radix based number systems. So we talked of this large number in the radix 10 or base 10. We also said, well, there are some insufficiencies when you want to represent this within 24 bits, right? Well, actually 23 bits if you remove the sign part. So insufficiencies, but the representational insufficiencies when you try to represent in binary form. Okay, so what makes binary different from decimal is this radix. And the key idea is that you have something called place value. So for example, if I give you 1, 1, 0, 1. Now in binary, how would you expand this? One into 2 raised to 3 plus 1 into 2 raised to 2 plus 0 into 2 raised to 1 plus 1 into 2 raised to 0. Okay, so this is a binary representation. So the place values here correspond to 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0. These are the place values. What's basically happening is the position will determine the exponent of 2 and that will give you the place value. So suppose I want to increase the place value, what do? I'll need a 0 to shift, right? A 0 symbol needed to shift the position of a symbol to increase place value. by a unit. So for example, in this here 2 raised to 0 is a 1, whereas if I want 2 raised to 1, that is 2, you will represent it as a 1 0. Now you could similarly talk about a decimal representation of this number 1101. So you could have 1 into 10 raised to 3 plus 1 into 10 raised to 2, just keeps moving up and down, plus, okay, give up, 0 into 10 raised to 1 plus 1 into 10 raised to 0. This moves up. Okay, so that is a decimal representation, and likewise you could talk about the place values in this decimal representation. Now we talked of decimal, which has 0 to 9, which are 10 symbols. Binary has 0 and 1, 2 symbols. In general, you could have R symbols. So if you have radix system R, you should have R symbols, and the value of symbol is multiplied by R for each left shift. Okay, so this is what you get as you shift left. 1 R, R square, R cube, and so on. Okay, and then you add them. So let's take the decimal system. Radix is 10, place values are 100, 110, 100, 1000, and so on. So if you have 346, you begin with leftmost bit 6, and then move to the right to 4 and 3 respectively. There is another system called hexadecimal system. A hexadecimal is interesting because it is related to binary system. It gives you a compact representation for binary representation, and it has a correspondence with a nibble. So we talked about the nibble in the last class. So the hexadecimal system has these 16 digits 0, 1, 2, 9, followed by A, B, C, D, E, F. So 16 of these. So 23, for example, you would write as follows. So first of all, 23 in hexadecimal is interpreted as follows. So value of 3 will be 3, and more specifically this corresponds to 3 into 16 raised to 0, right? And 2, the second thing that we process, the digit here, is 2 into 16 raised to 1. So you sum up 32, that is 16 into 2 plus and 3, oh, this is 35, I thought I corrected it, 35, that is the value in decimal. So 23 in hexadecimal corresponds to a much larger value in decimal, obviously because you are allowed to use lot more symbols. We of course did use only 2 and 3, but the 3 could have potentially gone up to F, and 2 could have potentially gone up to F again. Let's look at 45171 in hexadecimal. Okay, so this is the value, I mean the expansion. We start again with the leftmost and then rightmost and move to the left. Let's try and see what the value is as as per our C++ program 45171. Okay, so now how do I represent hexadecimal? I'll put a 0x prefix. Int hex number is 0x. Is this visible? So 0x45171, that's my representation. However, when I do a cout, it's going to print this number in decimal because, first of all, cout reads cout is supposed to interpret things in the decimal form. What happens at the level of the hardware is that 0x45171 is stored as a sequence of bits. Because there are three things happening here. So 0x45171 that you see on the screen or the console in hardware will be represented as a bits, right? It's all in terms of bits. Now you could actually write this as how many bits, or by you can think of it as bytes. 71. Now it's important to understand this. So 16, each of these 16 would correspond to sequence of bytes. Sequence of bits. So let me use the left hand side for the representation. So 0 is of course 0000, 1 is 0001. F, what would it correspond to? The value it's supposed to represent is 15 in decimal, right? So its representation is 1111. Is that correct? Okay, so you could think of the hexadecimal representation as giving you 4-bit subsections of your entire binary representation. Okay, so now coming back to 0x45171. So this one is 0001. This 7 is, can help me? 0111. Is that correct? This is 0001. 5 is 0101. 4 is 0100, right? So in hardware, this hex is going to be written this way. I know you can easily see that the correspondence helps. Right, but since we are all too familiar with the decimal representation for multiple reasons, we are also comfortable with it. When you ask a C programming execution environment to try and print it, what do you get? Let's just run this program, compile and run it. So 282993. Okay, so this is what is happening. 282993 in decimal. So hexadecimal has a special place. There's an explicit way in which you can assign int to some hexadecimal value, but and then you do it in hexadecimal, you're actually representing it in binary value only. It's a more compact binary representation. Okay, so right, and we all already seen why binary is intuitive. You're just dealing with two levels, two voltage levels for the representation itself, and voltage above 5 volt is 1, and between 0 and 0.2 is number 0. Right, so this is the high value corresponding to 1, there's a low output corresponding to a 0, and this is a transistor being shown in saturation. And we already saw that more levels would actually lead to complications in representation. You will not be very robust to fluctuations in voltage. The storage itself also happens through electric charges on capacitor, right? So binary is therefore very has been largely convenience. So quick recap: binary, you are invoking a radix of 2, you need only 2 digits 0 and 1, and the place values correspond to 2 raised to 0, 2 raised to 1 and so on. You have seen how you could represent, how you could look at the binary value, the decimal value corresponding to binary. So 1 1, if it's written in binary, would correspond to 3 in decimal, or 1 1 0 0 1 1 is 51. We could also go the other way. Somebody asked this question, right? How do you find the binary representation for a decimal value? So how do I go from a value of 51 to its binary representation 1 1 0 0 1 1? What would you do? Yes? Yeah, so like you to think, suggest answers. Maybe try and write down the steps. Won't spend too much time, just the rough idea. Divide by 32. So what you're talking about is the largest power of 2, which is less than that number. So you start with 32. Okay, so you look at powers of 2, and that's why place values become important. So the largest power of 2 less than 51 is 32. Divide it, look at the quotient. Then of course what you have to deal with is a remainder. So quotient will give you this 1. Then the remainder will be what? 19. And what's the next largest value? Next largest power? 16. So that gives you this second one. And again you look at the remainder, 3, 16 minus 19 minus 16, and again you look at the same thing, largest power which is less than 3, that is 2. Okay, so that basically means that these all will be 0. So 2 is basically 1 0, right? So you have already jumped, and then again you'll have remainder 1 that corresponds to 2 raised to 0. Okay, so roughly that's how we do it. So you could do decimal to binary conversion thus. So example 154 in binary, look at the steps, you will do the same thing, largest powers less than the subsequent remainders starting with the original number. Okay, and the place values handy to have alongside as you proceed. You could also represent fractions in binary. So the place values will basically now diminish. So 0.1 in binary will mean 0 plus 1 into 2 raised to minus 1. So this 2 raised to minus 1, first place value, then 2 raised to minus 2, that is 1 by 4 is the second place value. So binary in 0.11 can be written thus. It will correspond to 0.75 in decimal. Okay, so it's very similar. Now we get to the other interesting part, sign. So non-negative numbers, we've been conveniently consuming all the bits to store non-negative numbers, right? So 8, 16, 32, 64, right? So to store 25 using 32 bits, what do you do? Well, I have all these zeros, 1 1 1, sorry 1 1 0 0 1, that's all. 1 1 0 1 0 0 1 is 25. You can follow, you can store the charge pattern shown there. So yeah, your range of all positive numbers with this representation is 0 to 2 raised to 32 minus 1. This is exactly what you get when you used an unsigned int. I showed this as a type earlier. This is a luxury you get. You can do an unsigned int, you can also do an unsigned long int if you want more space, more representativeness. However, what do you do with negative numbers? What if I had to represent minus 25? Negative integers. Let's just talk about negative integers. Minus 25, what would you do? Yes? I thought we've already given hints. What would you change in this representation? Okay, so what's one naive way? Give me a simple hack here. So to store negative, you could just use the, you could just flip the first bit. So this is what you could do to store, say minus, right? So one of the bits can be used to store the sign. So sign bit is 0 means positive, sign bit is 1 means negative number, right? So minus 25, that's one small change we have made here. Now suddenly the range has shrunk. Well, the range of positive numbers has shrunk. So what you have is only 31 bits for storing the actual value, the magnitude. So you have minus of 2 raised to 31 minus 1 to 2 raised to 31 minus 1. Are you happy with the solution? How many of you are happy with the solution? How many are not happy with the solution? But let me ask you a more specific question to put you in little unease. So how about 0? How will you store 0? Is there a single way of storing 0 here or multiple ways? So what are the multiple ways? You could have minus 0 or 0, right? Just everything is 0 except for the first bit. We are not happy with this solution. Okay, so let's do this quick exercise. So we have the 0, 0, 0, 0. Let's just take 4 bits, the inspired by hexadecimal. That corresponds to 0. 0, 0, 0, 1 is 1. 0, 0, 0, so 1, 0 is 2. 0, 1, 0, 0. I'm sorry. 0, 0, 1, 1 is 3. 0, 1, 0, 0 is 4. I'll need more space here. 0, 1, 0, 1 is 5. 0, 1, 1, 0, 6. 0, 1, 1, 1 is 7. Okay. So this is fine. The problem is when you have a negative, so let's say I put 1, 0, 0, 0. That lead to what? What is that supposed to be? Minus 1. Oh, sorry, minus 0. And we are unhappy about it. Right? This is a problem. Why is it a problem? Well, if I have to do equality, x equals y, and x is 0, y equals minus 0. Imagine the amount of hard work we have to do in our wiring to kind of check for equality at special case for 0. Other equalities are all simple. This equality is special case. This is not very good for us, and we are honestly losing one configuration. I mean, this is redundant. Let's look at a slightly different representation. I will push this guy up, promote him, or promote, demote, right? Depends on what your goal in life is. So what I'll do with 1 0 0 0 is I'll say, oh, let me put 1 0 0 0 as minus 8. Somehow fell from the sky, right? And then from there on I will increase. So this is anyway supposed to be negative, but instead of making it as minus 0, I'll call it a minus 8. And then I'll say, well, let me keep increasing the other values, and minus 8 will become minus 7, minus 6 and so on. So 1 0 0 1 minus 7, then 0 1 1 0 1 0 will become minus 6, one 0 1 1 will becomes minus 5, and then please help me, 1 0 1 1 0 0 will become minus 4, 1 1 0 1 minus 3, 1 1 1 0 minus 2, 1 1 1 1 will become minus 1. All I did, this part is the same, all I did was change my starting point for the negatives, and that I set to 1 0 0 0. So if you just look at, ignore the first bit, it just makes sense. You start with the smallest value, the most negative value, and then move on. Okay, this is the negative numbers. Now this has some interesting properties. Okay, it's not really arbitrary. There is something called the 2's complement. Okay, before we get there, I want you to do a small exercise. So do the following, add any, all of you independently, add any number and its negative and tell me what, so all of you know how to do addition of two binary numbers. If you don't, you'll learn it. So add a number and its negative and tell me what the value is. No discussion, I would like every neighbor to have a different choice. So if you add 5 and minus 5, your neighbor should be adding 6 and minus 6. Yeah, so we are only looking at 4 bits. Minus 25 will require more. 8 bits, for example. Yeah. So first of all, in the board I have used how many bits? This is 32 bits. How many bits have I used? 32, right? What I have on the board is just 8 bits. All I am trying to tell you is the spirit of the expression, because I can't really write 32 bits and illustrate on the board. Okay, but yes, the same principle holds. You're right. So please do the exercise of adding a number and its negative and tell me what the value is. Why? No. So that is not that. On the screen, I have not shown 2's complement. On the screen, I have just shown the previous proposal.
Okay. This isn't the right.
This is a previous proposal. I am moving to the next proposal. And this is where we began, and I said I am not happy with an ambiguity for 0, right? Okay, so make sure that neighbors are not summing the same x and minus x. What did you sum? Oh, okay. So some of you need help in adding binary numbers. Let me take one pair for your convenience. So let me take 6, 0, 1, 1, 0, and to that let me add minus 6, 1, 0, 1, 0. The addition is pretty much the way you have for decimal numbers, except that what you carry forward will be only a 0 or a 1. So what does 0 plus 0 amount to? What does 1 plus 1 amount to? 1 plus 1 is 1 0. 1 plus 1 is 1 0. So you'll have a 0 and a 1 carried forward. Is that somebody had difficulty, right? This is how you would carry forward. You will carry forward a 1. This 1 plus this 1 is 1 0 again, a 0, carry forward 1. Okay. Did everyone get, if you're not finish it, but whoever has computed, did you get the same sum? The number is negative, add up to the same value. So x plus minus x in this representation will add to this 2 raised to 4, no 2 raised to, this is 4, right? 2 raised to 4, 16. These are 4 bits. How many of you got this? How many of you are able to get this addition to be 2 raised to 4? The rest please make sure that you pick a value and kind of ensure. This is the same idea for any other summation. So this method, what you're basically doing is representing minus x as 2 raised to 4 minus x. Okay, so the spirit is here. If x is positive, the binary form of x is the x, no difference. If x is negative, the binary form is 2 raised to n plus x. Okay, so minus 25 now we have shown in 2's complement. Someone was saying, well, this previous representation is not 2's complement. The previous representation is the old one. Now for the old one, we have moved to the new one. Now one reason it's called 2's complement, this representation is called 2's complement, is that this x plus minus 1 minus x equals 2 raised to n, 2 raised to n in general, right, if you have n bits. So this gives you a very clean way of recovering x from, or minus x from x. Okay, so let's look at a procedure. So I'll tell you the procedure, you can verify it. Step 1, flip every bit of the binary representation of x. Okay, so let's take the example of 6, 0, 1, 1, 0. The first step is 0, 1, 1, 0 becomes 1, 0, 0, 1. Flip every bit. Step number 2, so this is the first step, is the 2 is basically complementing. Step number 2, add 1 to result of step 1. Just add a 1 to the result of step 1. So you will do 0, 1, 1, 0, to that you add a 1. Just see what happens. Sorry, I meant this part, the flipped value, 1, 0, 0, 1, you add a 1 to it. What is the result? So you'll have a 1 plus 1 equals 0, and 1 carried forward here, right? So the result will be 0, 1, 1, 0, 1, 0. Okay. So this step basically gives you, these two steps give you the representation for, the binary representation for the negative of any number x. And this is exactly corresponding to this expression. I mean, x, the representation of x and the representation of minus x in binary form. Right, so the representation of x in binary form and the representation of minus x in binary form sum up to 2 raised to n. Okay, so this is the 2's complement wrap around. Whatever we wrote on board, it's like summarized in the table, and you can verify 2 things. One is you can get minus x representation from x using the 2 steps, and the fact that representation of x and minus x sum up to 1, 0. 2 raised to n, 1 followed by n minus 1 zeros. Now, what's really happening here is as follows. I'll conclude with this slide. So you have some kind of a continuity here between minus 1 and 0. You can go from minus 1 to 0, from a negative value to 0 by just flipping every bit. Makes sense? From minus 1 to 0, all you need to do is flip. However, there is a jump from the max value, right? The max value here 0, 1, 1, 1, that max value, and the min value which is 1, 0, 0, 0, there is a big jump. So there's a jump here. Okay, so that probably is the only kind of hazy thing here. Why should there be a jump, right? I mean, the jump, what I meant is the jump is in the value of the decimal representation. Binary representation is actually not a jump. Max value 0, 1, 1, 1, add a 1 to it, you'll actually get to 1, 0, 0, 0, right? So there is an inconsistency of some sort. The max and the min values are only one bit apart, whereas the representations being one apart doesn't amount to they being neighborhood, because the max and min are the most separated. Okay. So this is a 2's complement wrap around illustrated.